Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems. In the last lecture we have seen how to not only obtain transfer functions of electrical systems, by which I mean essentially electrical circuits, but we have also seen how we can solve for variables within that electrical circuit such as voltages and currents. So essentially we have seen how transfer functions are useful in obtaining the zero state solutions, right, and we have also seen how we can use the Laplace transform to also solve for the zero input solution, and we have seen the overall solution of the differential equation is nothing but the sum of the zero input solution and the zero state solution, right. So before we move on to other kinds of systems, because essentially what we are now trying to look at in this course is modeling of various dynamical systems. We have already seen electrical systems to that end. Now we shall move over to mechanical systems, but before that here are a few problems for you to practice and sharpen your skills and ensure that you have actually grasped whatever has been discussed so far. So on the slides you can now see some practice problems for you. So provided you can write down the solutions to these problems, you can safely assume that you are kind of in a situation to move over to the next topic, which is going to be mechanical systems. So of course here the first problem gives you a bunch of transfer functions whose inverse Laplace transforms are asked here in this question. In the second question you have to of course write down the KCL and KVL equations for these circuits, right. Of course this circuit you might see it is not a planar circuit, so you might have to use some graph, right, to denote different nodes and edges, right, as we have already seen in one of the practice problems. And finally here you have the example of a non-ideal op amp, and you have to solve for the transfer function between V out and V in. So of course you cannot make the idealization assumptions such as infinite input impedance, zero output impedance and infinite gain. Those are all finite numbers or non-zero numbers as the case may be in this problem, and you have to still obtain the transfer function for this system. So hope you enjoy solving these problems, and when you are ready we will move over to the next part, which is modeling mechanical systems. So of course there can be a plethora of different kinds of mechanical systems. We will precisely look at two different kinds, one characterized by translational motion, the other by rotational motion, right, and thereafter we will move over to electromechanical systems. Of course that will form the content for another lecture some other day, but for now let us see what we essentially mean by modeling these mechanical systems, right. So let us take the simplest case of a mass like so, okay, of M, which is connected by a spring to the datum. So spring has a spring constant of K and also a dashpot which essentially provides friction. So we denote this by B. So this dashpot, the force in this is proportional to the velocity with which the mass is moving, and let us say there is an externally applied force here to this mass. So how do you write down the equation of motion of this body? Of course we have learned this in our high school physics. We have to use free body diagrams. So let us draw the free body diagram of this mass M, since there are no forces applied, no motions in the vertical direction. So we will only draw the free body diagram for the x direction. So this is of course the applied force. So if you have detached it from the spring and the dashpot, then you have to replace them with equivalent forces in the opposite direction. So suppose this mass is moving, is displaced by x units to the left. In that case, the force exerted by the spring is one of tension, attraction to the right, and similarly the force exerted by the dashpot is proportional to the velocity and given by bx dot, like so. So of course if x is in this direction, you will naturally have x dot also in this same direction, right. So now if you want to write down the equation, then what do we need to do? Of course you know by Newton's law that every action has an equal and opposite reaction, so you consider a pseudo force which is mx double dot, right. Once you apply the pseudo force, you can consider this body to be in a state of static equilibrium. So therefore you can now write the static equilibrium equation for this body as follows. So F, which is this, the externally applied force, which is balanced by mx double dot plus bx dot plus kx, right. And now without much ado, as we are used to doing by now, we shall take Laplace transform on both sides and replace these variables of interest with their uppercase variables or capital lettered variables. So this is f of s, which is the transformed force in the Laplace domain. Then you have ms squared xs. Of course we will assume that the initial conditions, that is the initial velocity and the initial positions, are 0, and therefore we don't need to bother with them while writing this differential equation, right. So here's what we have, all right. Now immediately notice something very interesting. If I pull out this x s times s, which is essentially nothing but the Laplace transform of velocity, right, because we know that when you are taking the derivative of a term in the time domain, it is the same as multiplying the term by s in the Laplace domain. So if I am taking the velocity out common, then what I have here is this, and this, I put it to you, should remind you of something that you are already familiar with, and this is the reason why we started with electrical systems, which we are sort of more familiar with, because we have seen things like impedances and admittances. We are as yet not familiar with such terms when dealing with mechanical systems, but now you can clearly see the analogues here, the analogy here. What is it? Let us consider this electrical circuit, which we have just considered in the previous lecture as well, the RLC circuit, which is excited by a voltage source like so. And we know that we wrote this corresponding differential equation, we wrote this as follows, in this manner. So I of s times, of course we treated them as impedances, so L replaced by SL, R replaced by R itself, and C replaced by 1 upon S times C, right. And now if you look at these two equations, if you try and compare them, something very interesting emerges. You can see that you can compare the force that is appearing here with this voltage here. So it's a force voltage analog. Similarly, you can compare this Laplace transform of the velocity with the Laplace transform of the current here, right. So it's as if these variables or these quantities are analogous. What is even more interesting is the fact that you now have these physical parameters, the mass, which can be compared to the inductance. You have the resistance, which can be compared to the dashpot, and you have the spring, which can be compared to the capacitance, or if you are particularly fastidious, I would say the reciprocal of the capacitance, which is incidentally termed as the elastance, right. Often you denote it by a variable d in electrical engineering. Never mind, we will not get into the nitty-gritties of that, but nevertheless you would struggle to miss this similarity between the two. This has, as it turns out, even greater implications if you think in a little more abstract sense, not very abstract, but a slightly more abstract take on this would be, look, mass and spring, they store energy. They are not sources of energy, but they store energy, they have the capacity to store energy. So a spring which is compressed or which is stretched stores energy, right? Similarly, a mass has inertia. On the other hand, a dashpot only dissipates energy in the same manner as a resistance dissipates energy in an electrical circuit. So even at a deep physical level, there is this analogy you see here, right? So we shall now see how connecting the analogy between the electrical circuit and the mechanical system will aid us in being able to write the equations for the mechanical system without always having to draw the free body diagram. Recall that when we were dealing with electrical systems, we did not always write individual mesh equations or node equations by always carefully calculating everything, right? We often did it by observation, as I might have remarked in a previous lecture. Now we are suggesting that the same thing can be done for a mechanical system if you understand what the analogy with the electrical circuit is like. So let us quickly try and take a look at one such example, and things will be hopefully a lot clearer. So consider a mass, a box such as this, okay. So suppose this is a box of mass, let us say 1 kg, m is equal to 1 kg. I will probably drop the units, yeah, we will just assume that the units are consistent. So we are not playing around with SI and other FPS and other units, okay. So let us call this another mass which is sitting within the box, but which is free to move inside this or slide inside this box. Let us say this is also 1 kg, right. Okay. Now the situation is such that there is a force applied to this mass sitting inside this open box, all right, and this entire setup is resting on a surface, on a plane, all right. So the reference for this, the movement of this mass m2, let me call this m1 and let me call this m2, that would be better, because then I can call this variable as x1, right. This is the displacement of the mass m1, and let us say this is the displacement of the mass m2, okay. With respect to a body fixed frame of reference, this is the displacement. I could have fixed this frame here, I could have fixed it here, it is just that I am sort of isolating the two a bit so that the figure does not look too cluttered, that is all, yeah, right. So now these are our displacements of the two masses m1 and m2 respectively. Now what is happening here is, I say that this is connected through a dashpot. So again this B, what should I call it? Let us say this B is B3 probably. So this B3 is again 1, I am not writing the unit, it will be actually Newton second per meter, but for want of space I am actually omitting that. And there is also a spring here which is again of 1, of course the unit will be Newton per meter, but again I am omitting the unit just so that the figure does not look cluttered. And there is also some force of friction acting here. So I will call this B2 is equal to 1, again Newton second per meter, and there is also friction acting on this surface which is essentially the same surface of the box. So that is B1 is equal to 1, all right. In addition, there is some force of friction which is acting on this surface too, which is only acting on m2, remember, not on m1, all right. So what we then say is that this friction acting on this surface is basically nothing but, I call it B4 is equal to 1 once again, okay. So basically this is going to be just proportional to the velocity or the speed of this block of m2, okay. Now it seems like a pretty complicated system, and let us say you have been asked, so the goal is to obtain the transfer function x2 of s over f of s. So what is the transfer function between the displacement of the mass m2 when the force Ft is applied to the mass m1. Okay. So let me first adopt the old fashioned method, which is to draw the free body diagram of the smaller mass m1. Okay. And I can quickly draw all of these things here. So suppose there is a force acting in this direction, which is f of t, right, and then of course I have the friction on this surface. It's proportional to the relative velocity, remember, because the surfaces in contact are those of m1 and m2. So the friction, that is B2, is not proportional to x1 dot alone, but rather on x1 dot minus x2 dot. Okay, that is what you have to notice carefully, because it's common to both the surfaces. Yeah, this is proportional to the relative velocity between these two surfaces, not the absolute velocity of the block mass m1, right. By the same token, you now look at this spring here. Of course, this block m1 moves by a displacement of x1, but the block x2 also moves by a displacement of x2. So the relative displacement is what counts for the spring. So the spring is going to oppose this force with something that's proportional to x1 minus x2. Similarly, you also have this B1 here, which is essentially like B2 itself. There's no difference in character of these two forces, it's just that they are acting on two different surfaces, the upper one and the lower surfaces, right. Okay. Is there anything else that needs to be accounted for? So we have accounted for B1, we have accounted for B2. Of course, there is this dashpot as well, right. So there is this dashpot as well, because I don't have space to put it here, I am putting it here. So again, that is also proportional to the relative velocity between m1 and m2. So I again write this as x1 dot minus x2 dot. Okay. And now if I want to balance this, if I want to put it in static equilibrium, I'll have to use the pseudo force, which is m1 x1 double dot. So clearly now balancing this force and writing this like a static equilibrium equation, what I'll then have is, in the Laplace domain, f of s balanced by s squared x1 s. Of course, we assume, as before always, the initial conditions to be 0. So you see what's the coefficient of x1 dot? B1 plus B2 plus B3, but they're all unity. So it's basically 3s x1s. I'm quickly doing this, all right. What about the coefficient of x1? It's just k1 appearing here, isn't it? So it's basically 1 times x1s. But what appears as the coefficient of x2? There's a reason why I'm doing this in a quick fashion, or I'm assembling together terms like this, and it will soon be clear. So let me cluster together all terms related to x1 here, and then I'll cluster together all terms related to x2 in the next block. So what are the terms related to x2? You see, where is x2 involved? Here, 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 and here. So of course, it's b1 plus b2 plus b3 times s times x2. So that's essentially 3s x2s, but it appears with a minus sign, remember, because of this minus sign here. Also, you have this k, so that is again unity, so that is x2s, right. So if I just go one step further, I'll just write it as s squared plus 3s plus 1 times x1s minus 3s plus 1 times x2s. What is the analogy? What is the similarity we see here? Remember, when we wrote those loop equations in the electrical circuit, right, if we treat these fellows, these displacements, or rather the velocities, if we take s times x common, right, what does this remind us of? This reminds us that in the electrical circuit, what we had here was the sum of the impedances in the entire loop, and what we had here with a negative sign sitting as the coefficient of x2 is basically the sum of the impedances that were common to loop 1 and loop 2. Do we see something similar over here? I wonder. Of course, things will be clearer when we write the equation of motion for m2 taken alone as a free body diagram, but I am arguing that I do not need to do that, and I leave it to you to check. You can actually draw independent, so take that as an exercise. You can draw the independent free body diagram for the mass m2, and I am claiming that it is going to be, so let us say this is equation 1. So the equation 2, which I urge you to check as part of an exercise, is from the free body diagram of m2, but I am going to write it very quickly, and the reason I am going to be able to do that is because I know the analogy with the electrical circuit. So what I know as the coefficient of x1 will be nothing but what was the coefficient of x2 here, of course with a minus sign. So this is very obvious. What needs a little more thought is basically the coefficient of x2 in the equation for m2, just like we needed a bit of thought for the equation of I2 in the loop for the current 2, right. So here each loop corresponds to each mass element, okay. So let us see what comes in inside this. What can we see inside this? Whatever's the total ensemble connected to this mass m2. What is connected to m2? This is 1, this is s, right. There's this one s over here, one s over here, right, and there is another additional s which is unique. Remember this b4, this is only acting depending on the velocity of mass 2, it is independent of mass 1, right. So therefore I will clearly have 4s and of course s squared, and I will have 1. So I put it to you to check that if you look for the free body diagram of m2, you will see the net connections, all the connections. There is one spring which corresponds to this. There are basically 4 sources of friction. One is b1, b2, b3 and b4. So that is basically 4. And there is one mass which is of course the mass itself, which is 1. Right. So this is going to be equation number 2. So again I will take the easy way out, and you work this out using Cramer's rule by eliminating or whatever you want to do, right. And if you can solve for this, you will see that eventually if you solve for these 2 equations that I have given you, you will find that x2 of s upon fs comes out to be 3s plus 1 divided by s cubed plus 7s squared plus 5, okay, s to the power 4 I believe, s to the power 4 plus 7s squared plus 5s, 7s cubed, sorry, plus 5s squared. Let me rewrite that, it's becoming a little clumsy, I just missed one power. It's s to the power 4 plus 7s cubed plus 5s squared plus s, okay. So that is the desired answer. Of course this should not be too difficult, you should be able to eliminate or use Cramer's rule between equations 1 and 2 and be able to obtain the ratio between x2 and f, right. So that is one part of it. Now what if I ask you to draw the equivalent electrical circuit for this mechanical system? Draw the equivalent electrical circuit. How would we do that? So let us take a look at these equations, let us focus on this, and again I have already discussed this, it is now a simple matter. Let me just rewrite the equation a bit, and that will make things easier to see the analogies, alright. So the first equation was of course f of s is equal to s x1s, because remember the current was analogous to the velocity, not the displacement, a minor point. Of course you can take the charge equivalent and then it will be the same, but okay. So then this becomes s plus 3 plus 1 over s, okay. I believe that is what it is, right, minus, if you take again x2s times s common outside, then you will have 3 plus 1 by s, okay. And in the second equation again you pull out s x1s and you have 3 plus 1 over s with a minus sign of course, and you have plus, let us pull out s times x2s again. So I am rewriting equations 1 and 2, nothing fancy about this, alright. So this is going to be S plus 4 plus S plus 4 plus 1 over S. So what does this tell us? Think of this as I1, this is I2 and this is I2, and think of this as voltage. So what about the first loop? What does the first loop contain? If I am drawing the first loop here, let me consider this to be f of s. Sum total of the impedance of the first loop is a 1 Henry impedance, a 1 Henry inductor, that is, this is a 3 ohm resistance and a 1 farad capacitance. But what is common to loop 2 and loop 1 is this 3 ohm resistance. So what is left that is unique to this first loop? Remember that this capacitance and this 3 ohm resistance are common to both loop 1 and loop 2. So all that is unique to loop 1 is the inductor. So let me draw this inductor 1, and then I draw whatever is common here. So this is 3 ohm, this is 1 Henry, and then I draw the capacitance. Of course, never mind what the size of a 1 farad capacitance in physical world would be like. This is just for a sake of analogy. What about the second? What is common to the second loop and this common connection here? The 3 ohm resistance and the 1 farad capacitance. If you take away the 3 ohm resistance and the 1 farad capacitance, you will still be left with a 1 Henry inductor and a 1 ohm resistance, right? So let me put that right away here, a 1 Henry inductor and a 1 ohm resistance here. And now if you call this as your S times X1 S, and if you call this current as your S times X2 S, voila, you have the equivalent electrical circuit for this mechanical system, which may not look very familiar, but if you are an electrical engineer, this circuit is really pretty commonplace. Nothing fancy about this circuit, is it, right? So we've shown you that this circuit is exactly depicting the same physical equation as this, okay? So there exists a one-to-one correspondence between the electrical circuit and this particular mechanical system. So hopefully you see the analogy. However, this is not the only form of analogy that can exist. Remember, we had, when dealing with electrical circuits, KVL as well as KCL. So we told you that when we are asked to determine unknown voltages, we use KCL, unknown node voltages. When we are asked to determine loop currents, we use KVL, Kirchhoff's voltage law, right? By the same token, you see that the series equivalent, when you have the series equivalent, you generally employ the KVL. Why do I say series equivalent generally employs KVL? Because you see, after all, what are these terms? These are basically, as you go around a loop, these are the impedances you encounter in series. For example, here also in this diagonal entries. So in the equation for loop 1, if you look at the coefficient of current 1, in the equation for loop 2, if you look at the coefficient of current 2, what you see is basically the series equivalent of the impedances across the entire loop, right? On the other hand, if you look at the KCL, when you write the node equations, you essentially take that node voltage to be the unknown and you consider all the edges that are connected to the node. It's as if you ground together the other ends of the edges. So it's basically a parallel equivalent. All the currents flowing into the node or away from the node. So those are like parallel paths all leading to that node. So I put it to you that the parallel equivalent is basically the KCL. It then stands to reason that if the electrical circuit, which is so analogous now that we've seen it to the mechanical system, right, should also have a parallel equivalent for the mechanical system, right? So what is this parallel equivalent? Let's try to understand the parallel equivalent for the electrical circuit first, over which we have a little bit better grasp, I assume, and then we shall see what it entails in terms of a mechanical circuit or a mechanical system, right? So for instance, consider a node such as this whose voltage, let's say, you're supposed to determine. So this is connected to, let's say, an inductor which is grounded. Let's say there is this current source that is feeding this, right? So there's a current flowing through here. Let's say there's a capacitor that's connected to this, which is also grounded, and let's say there's a resistance which is also grounded. Now, if you want to write down the node voltage, okay, this is a hybrid notation sort of, right? It's like a sort of hybrid notation. Let me call it Vt. Let me not write this as V of S and mix together two. So let me call this V of t, small v, right? Now, if I want to write the equation, the node equation in the Laplace transform domain, what should I write? Yeah, what is basically the sum total of the current flowing into this node? That is nothing but I of S. And what is the sum total of the currents, let us say, flowing out of this node? So, if this is considered to be at a higher potential with respect to the ground, then the current flowing through this branch is nothing but V, okay, let me write that as capital V instead of small v, because now we are in the transform domain. So, V of S minus 0 over SL plus V of S minus 0 over R, which is this current, right. So, let me connect the currents to these terms here. This is this current, this is this current, and the third term would be plus V of S minus 0 upon 1 upon SC. Remember, these are the impedances by the respective elements. SL is the impedance due to inductor, R is the impedance due to resistance, 1 by SC is the impedance due to the capacitance, right. So, now if I write this down in a simplified fashion, what I have is IS, when your driving force is a current, you can write this equation as 1 by SL plus 1 by R plus SC. But this, it turns out, is also similar to the equation that we had written a while ago for this mechanical system, right, is it not? You see, where is it? Yes, here this is, right. If you look at this now, so let me write that down again instead of being a little lazy and clumsy about it. Recall. So, this is what we recall from the preliminary diagram, that is this diagram, okay. So, let me mark it out with a blue pen. Recall later, yeah, and this is where we recall this, okay, right. So, what can we write this as? This was nothing but, you see, S times XS, and what we had was MS plus B plus K upon S. So, now you see the analogues have changed. What has happened now? The inductor is now like the spring, the capacitor is now like the mass, but the resistance or its conductance is still the same as this fellow here, which is the dashpot. And this is not surprising. You see, as I told you earlier also, from a physical perspective, both the inductor and capacitor are energy storage elements. So, you might as well interchange one with the other, it does not matter, they have both essentially the same nature, right. But you see, still the common factor remains, the dissipating unit, the resistance is still analogous to the dashpot. Not surprising, is it, at all. So, therefore, this analogy is between a current and a force and a voltage and a velocity, all right. So, this is a more physical insight, is I am just claiming here, I will substantiate that shortly, more physical insight is retained in this parallel equivalent. So, since I have not named it formally, let me just say that where what we had over here, yeah, this was basically a series equivalent, okay. But here what we have is a parallel equivalent. So, why am I saying that more physical insight is retained in this parallel equivalent? Yeah, I should be able to justify this in some way, isn't it? Before going into that, let me just draw the equivalent parallel circuit. So, we have seen this is a series equivalent circuit. So, let me just mark this now, this is the series equivalent circuit for the mechanical system. Let me put in a little more effort and draw the parallel equivalent circuit for the same set of, this same bunch of equations, yeah. So now our goal is to get the parallel equivalent for this. So notice, what is the parallel equivalent, what is the principle behind drawing parallel equivalent? You have of course a current source replacing a voltage source in the parallel equivalent. So the first thing I draw is a current source, and what is the current source analogous to? We have seen that the current source is analogous to the force. So I will just put this f of s here, and now where does this current go? It goes into parallel branches, it is balanced, right? That is what KCL is, like we had here, this should be balanced. So how do we see the KCL equivalent of this system of equations? You see now the analogues have changed. This is now the current, this is now what? This is now my voltage, right? And these, instead of being impedances, yeah, these are now admittances. So what is the coefficient of voltage 1 in the node equation for V1? What is the coefficient of voltage 1 in the node equation for V1? Recall, we had said that it is the sum total of all admittances of all those branches which are incident at node 1. By the same token, what is the coefficient of V2 in the equation for node 2? What is the coefficient of voltage 2 in the equation for node 2? It is the sum total of all the admittances of all the branches that are incident at node 2. Very similar, isn't it? If you just figure out, give it a moment's thought. What about the cross terms? In other words, what is the coefficient of voltage 2 in the equation for node 1? It is precisely the admittance that is common, or that is shared between node 1 and node 2. What does that mean? It is the admittance of all the edges or all the branches that are connecting node 1 and node 2, right? Pretty simple, isn't it? So now all these terms, instead of treating them as impedances, we now treat them as admittances, keeping in mind that this is how the admittances look. So wherever we have 1 by s like terms, we should replace them by inductors. Wherever we have constant terms, we should replace them by resistances for suitable value. Wherever we have terms whose coefficients are s, we should replace them by capacitors. So now, keeping that in mind, what we can then write is the following. So consider, for example, let us call this node 1, right? So let us call this V1. Right. So let me first, like I draw loops first while writing KVL, here I will draw nodes first. So let me call this node 2, okay, let us not call it V1, let us call this in the transform domain, and let us call this Sx1, S, and let us call this Sx2S, right. So of course, from the first equation I know that node 1 is fed by a current source which is Fs. And what are the sum total of everything that is incident on node 1? It is S, yeah. What is S analogous to? S is analogous to a capacitance. So it is basically a 1 farad capacitance, a 1/3 ohm resistance, and a 1 Henry inductor, out of which this 1/3 ohm resistance and this 1 Henry inductor are shared with node 2. So basically, if I want to draw the connection between node 1 and node 2, I must have a common inductor, yeah, because 1 by s, remember, corresponds to an inductor like term here. So I share this inductor. So this is of course a 1 Henry inductor, and I share a 1/3 ohm resistance between node 1 and node 2, right. But what is exclusive? What is indeed exclusive? After all this is done, all this common factor is taken care of, what is exclusive to node 1? Remember, it is this capacitance, right. So I have to still connect a 1 farad capacitance which is incident on node 1, but which is not shared with node 2. So let me draw that 1 farad capacitance here, right. Yeah, okay. What about node 2? Look at the equation for node 2. If you look at the equation for node 2, you see that you have a 1/4, right. So what should my resistance be now? So I should have some resistance here, right. So what I am going to do here is look at this difference, Sx3 minus Sx2 divided by 1/3, so that is 3 times, right, and then I have Sx2 minus 0 by 1, so that gives me 4 times, isn't it. So what I want is basically the coefficient of this to be 4, what I want is a coefficient of 4 here. So I already have a coefficient of 3, so I need another coefficient 1, so I need 1 by r is equal to 1, so which is basically telling me that r has to be 1, right. So therefore I put it to you that this is actually the equivalent. Of course I need to also add some capacitance, right, because remember this capacitance, yeah, this capacitance, this wasn't common here, so I have to have this S too, yeah. So this 1 farad capacitance I have to have in common. So now look, notice what about node 2 here, this is node 2, this is node 1, the sum total of all the admittances to node 2, what is it? If you take this 1/3, right, so 1 by 1/3 plus 1 by 1, that is the total resistance, right. What is the sum of the impedances? So it is basically 1 Henry, that is the L. What is the sum total of all the capacitances? It is 1 farad, that is the total C. So doesn't that match up to this coefficient here? You see, this is the total resistance, this is corresponding to the total inductance, this is corresponding to the total capacitance, out of which this much resistance is common shared with node 1 and this much inductance is also common and shared with node 1, yeah. So that is what we have shown here. So this is exactly the same circuit, this parallel equivalent is depicting the same differential equation as this circuit which was depicting the series equivalent, okay. So we have basically seen that there are these analogies between the parallel equivalent and the series equivalent of a circuit, right. So there is another fine point that needs a bit of elaboration here. The analogies between these two go beyond this, just this series and parallel equivalences or whatever we are putting on board here, okay. There is another thing where the physical insight will help us, and particularly this parallel equivalent will help us. So most often in your textbooks or in most problems you will encounter, you will see that this dashpot and this spring, they are connected mostly in parallel. So you know that the overall displacement of this dashpot and the spring is identical, isn't it. So this is x. So you can clearly write that F, if this is the F that is applied, then you can clearly write this F is equal to nothing but Bx dot plus Kx. So this is when they are put in parallel. But now suppose by some by some stroke of luck, or if you call it bad luck, you encounter a system where they are put in series like this. How do you get the equivalent then? And it turns out that having an understanding of this through and across variable analogy is going to help us. What is this through and across variable? Think of an electrical circuit, yeah. What happens in an electrical circuit? The current flows through the circuit, the voltage is measured across the elements of the circuit. So the current flows through the elements of the circuit, voltage is measured across the elements of the circuit. If you now think of something analogous in this mechanical system, for instance, what happens here? The force that is transmitted across this is exactly the same that is here, and it is divided into these two, right. Similarly here, the force that is transmitted here is the same as the force that is transmitted here, and the same throughout in a series path. It is exactly like when you solve problems on pulleys, right, lossless pulleys when you had, so you had this tension here and you had this tension here, so the same tension on either side of the pulley, right. So tension is nothing but a force. So force happens to be the perfect analog of a through variable, which is a current, which is another reason why we are so fond of this parallel analog, okay, because it helps restore the physical correspondence between these two, right. Now let us see what happens here in this case. So here clearly the displacement caused to this dashpot and that to this spring are not the same, they can't be, isn't it, because the force acting on them is the same, but there is no guarantee that the displacement should also be the same. In fact, this is very much exactly like the voltage. So if you pass, if you have a fixed current source like you have here, right, and if you pass this current through multiple elements in series, then the voltage drops across those elements will be commensurate to the impedances offered by those elements, is it not? So therefore, by the same token, if we now just replace this, like we replaced inductors with SL, we replaced capacitors with 1 by SC, similarly if you replace this in the transform domain, this with K, and if you replace this with BS, right, where S is the Laplace operator of course, then you see what comes of this. In the transform domain you can see that the force is nothing but K times, let us call this displacement x1 and let us call this displacement x2, it is the analog of a voltage, okay. Of course you can also take it to be the derivative of the voltage, whatever. So anyway, so what we then have is this force Fs is balanced within this spring by K x1s. At the same time, this force Fs, which is a through variable, right, is resulting in a displacement of x2 in this dashpot and is balanced by Bs times x2s. So from these two equations you can then write that f of s upon k is equal to x1s and f of s upon Bs is equal to x2s. So now if you want to find out what is the total displacement, so the total displacement, like the sum of the total voltages across series elements, here also the total displacement of both these elements is equal to the sum of the displacement of the individual elements, that is nothing but x1 plus x2. So we know that x1s plus x2s is given by f of s, and we can take this common and write this as 1 by k plus 1 by Bs, right. So that gives us this f of s times Bs plus k upon kbs, right. So that actually gives us a resultant relationship, you see. So you can exactly treat them like series parallel analogues. That is the beauty of this abstraction or this parallel analog or this analog we have drawn with the electrical circuit here, right. So that is why we are so keen on doing all of this analogies or seeing all of these analogies here. So we can just write then that x of s over f of s is then given by this sort of a transfer function for a mechanical system like so, where you put a spring and a dashpot in series. So now there is absolutely no impediment to you putting arbitrary objects in series and parallel. However, there is one catch, and I would like to close on this note. In the next lecture we shall see rotational systems, but before that I would like to warn you about something, about going too far with this analogy. You see, a few years back, about maybe a few decades back, a couple of decades back or so, there was this interesting paper which appeared in the IEEE Transactions on Automatic Control, and it talked about something called an inerter, okay, to replace the mass. Now notice very carefully here, when you talk about this series equivalent or this KVL equivalent, what happens indeed to inductors? You see, the inductors can never be shared between two loops. The inductor has to always be either connected to the source or it has to be always connected through other elements and then grounded, but it can never be shared between loops. Similarly, if you talk about the parallel equivalent, you will see that the capacitor has to be always grounded here, right. The capacitor can never be shared between two of these nodes, but in an electrical circuit we know that we can always have capacitors and inductors arbitrarily shared, right. So it turns out that even though every mechanical system can have an electrical analog, not every electrical circuit can be massaged into some equivalent looking mechanical system, because of the fact that masses, and here is the catch, here is where the analogy breaks down somewhat. A mass cannot be shared, okay. So for instance, in the KVL equations, when you are writing for electrical circuits, you take the number of loops to be dependent on the structure of the circuit itself, right. You look at the number of loops physically and you count the number of loops and you say that many loop equations you will have to write. But in the mechanical system, the number of equations you write is governed by the number of masses. So a mass cannot be shared between two different equations, if I may put it loosely that way, right. So you look at this equation for instance, yeah. You look at this equation, m1 appears only attached with x1, m1 does not appear attached with x2, right. So this, and there are several other such subtle points which necessarily imply that not all three elements, yeah, in the electrical circuits can always have a mechanical equivalent. So in this paper that I just spoke about that appeared in IIT Transactions on Automatic Control, where they introduced this inverter, they proposed that this inverter is actually the equivalent of a capacitor in the parallel equivalent, or the equivalent of an inductor in the series circuit, okay. The mass is not really an exact equivalent, okay. So I want you to just bear that subtle point in mind, and I hope that you found this little bit of trivia for now interesting. If you are interested, you can actually search for this inverter on the internet and you can actually come across the original paper that appeared in IEEE Transactions on Automatic Control and find out more about the motivation behind what this inverter is, and they actually invented this inverter, and if I am not mistaken they actually patented it. So that is a very practical application of control systems at work there, you see. So I hope that this has convinced you that not only what we are doing here is applicable to modeling of systems, but also maybe someday inspire you to invent things in practice and maybe earn patents for them. On that positive note, we'd like to end today's lecture. Until next time, thank you all.